Sequitur Labs CoreT is a secure operating system that provides a secure foundation for next-generation IoT devices. CoreT protects devices, data, and transactions. CoreT uses ARM Trust Zone, a proven hardware security technology that is used in chips on billions of devices, such as set-top boxes, ATMs, and mobile phones. IoT devices and applications using Trust Zone are better protected from malware and other attacks. The Trust Zone provides a secure processing domain that we'll call the secure world, one that is physically isolated by hardware from the normal world that runs a rich operating system like Android or Linux. This secure world extends beyond the CPU, its memory and software, to include secure transactions on a bus, interrupts, and peripheral functions within a chip. CoreT uses Trust Zone's hardware-based isolation capability. This enables embedded device makers to implement secure processes, such as secure boot and secure firmware update. It enables developing hardware-secured applications, stores data and encryption keys securely, and safely performs secure transactions. Operating systems such as Linux and Android run in the normal world. CoreT runs in the secure world and manages switching between the secure and normal worlds. This switch is accomplished by a secure monitor. CoreT's key features include secure boot, secure peripherals, reliable and concurrent execution of critical processes, key management, trusted firmware-based applications, validated rich operating system applications, secure input and display. The two demonstrations you are about to see illustrate three key features of CoreT. The first demo showcases the ability to keep critical processes running while the normal world rich operating system fails. In this case, the normal world operating system is Linux. The second demo shows how CoreT can be used to maintain device integrity. CoreT uses Atmel's ICM technology to detect malware that compromises the normal world operating environment. Here we have the Atmel Smart SAM A5D2, which is an ARM Cortex-A based processor, with CoreT running inside the Trust Zone. On the right side of the large screen, we have a console for the secure world running CoreT. On the left, we have a console showing the normal world running Linux. Each of the small LCDs shows a counter. You see Linux incrementing a counter on this LCD screen. This is an I2C peripheral whose driver is running in Linux. This LCD is a secure display. It is secure because it is connected to a secure I2C bus and its driver is running in CoreT. CoreT increments a counter on this LCD. It also shows the number of times Linux has been restarted. This button causes Linux to crash. CoreT runs a watchdog program that Linux must update. If any operating system failure within Linux prevents this update, then CoreT catches the failure and restarts Linux. As we press this button, you'll see a visible crash followed by CoreT's catch of the Linux failure. You'll notice the Linux counter has stopped incrementing. The secure LCD displays the detected Linux failure. However, the secure world counter continues to run and is unaffected by the failure within Linux. The Linux counter is frozen until the Linux reboots. And you can see Linux is beginning to restart. The counter then resets to 0 and begins incrementing once Linux has restarted. You'll notice the Linux reset counter in the secure world increments by 1 each time Linux is restarted. This shows the number of resets since the board was powered up. The Atmel Smart SAM A5D2 has a hardware security feature called the Integrity Check Monitor, or ICM. The ICM constantly watches for changes in the Linux kernel or other code in the normal world. The driver for ICM securely runs in CoreT outside of Linux. This enables CoreT to respond in case ICM detects changes in the protected areas of RAM. Remediation occurs as defined, and in this case, CoreT is configured to boot to the last verified image of Linux stored in flash memory. This image is stored as an encrypted file. CoreT loads the encrypted image and decrypts it prior to reboot. This ensures that the firmware is always protected. We can simulate a remote code injection exploit via a mobile app. This results in a change to one of the protected or monitored regions of memory. We press this button on the mobile phone to activate the malicious app. You'll see the malicious exploit has been activated in Linux. The ICM has now caught that malicious code injection, as indicated by the smaller LCD screen turning red. CoreT takes remedial action by rebooting Linux. You'll notice the Linux counter has stopped incrementing and is now resetting. The counter resets to 0 and begins incrementing once Linux has restarted. Linux is now running with the last verified image before the code injection occurred. CoreT runs a defined remedial action once malicious code is detected by the ICM. The remediation process boots Linux with a known image without impacting critical processes in the secure world.